we shall continue in this lecture the hydrogen molecule, a 2 electron 2 nuclei 4 particle system, and it is also the first system elementary which brings in the electron electron repulsion to the fore of chemical bonding. This is in large electron multi electron system. It is often referred to as the electron correlation term due to many pairs of electron repulsions, and it is an extremely important term, particularly Coulombic energy term for chemical bonding aspects. We shall look at the hydrogen molecule ion, hydrogen molecule in a simple manner following 2 elementary treatments, and later on indicate what are the developments when one considers the molecular motion in a more complete fashion, including the spectroscopic kind of terms, that is the nuclear motion, kinetic energy terms and so on. But for today's lecture and also probably the lecture that follows, we shall operate on the Born-Oppenheimer approximation and assume that the nuclei are stationary. So this lecture, hydrogen molecule, we shall look at it with the help of 2 broad pictures, 2 broad theories. The valence bond theory or valence bond method, often called VB method, first proposed by Heitler, Walter Heitler, I think. I have to check my history. Walter Heitler and Fritz London, 1927, the year when Born and Oppenheimer also published the approximation for molecular systems and for solving the Schrodinger equation. Okay. Their idea is to use the picture that chemists had until then, namely that the electrons are shared between nuclei. You might recall from elementary chemistry that G.N. Lewis, Gilbert Newton Lewis, the most famous American chemist in the early 20th century, who came up with the octet rule and also many other theoretical methods for the study of valence in chemistry, pre-quantum mechanical, and who was also well known as a thermodynamicist and who wrote probably the best known thermodynamics book in chemical thermodynamics, the book by Lewis and Randall, which is very famous and which has been revised by his colleagues Kenneth Pitzer and Brewer. It is G.N. Lewis who had this idea of sharing of the electrons between the atoms, and you might remember the dot pictures. The valence bond method is somewhat closely associated with this idea that the electron pair is localized. And in bonding, the electron pair finds most of its time between the bond distances. The other method, which we talked about in the hydrogen molecule ion, the molecular orbital method, the MO processes. Molecular orbital assumes that the electron is more like the electron density being shared all around the molecule using or in a molecular orbital, which is a linear combination of the atomic orbitals, the constituent atomic orbitals. We will not discuss the differences between the two approaches here. First, let us study what these approaches are, and then later on, as we progress further into quantum chemistry and more details, we can worry about which method is better for which system, or if there is any one single method and so on. Most of the time today, of course, people worry about using the linear combination of atomic orbitals, but not even the atomic orbitals that were first proposed for the hydrogen atom, something else, as I have been telling you earlier. They use the Gaussian orbitals, and then there are other methods for calculating. But these theories, the VB and the MO theories, give you in essence the philosophical thinking that went on at the time when computers were not available, and at the time, I mean, unfortunately I may say so, and I am not going to invite friendly criticisms from my colleagues, that chemistry being turned into a more like a computational machine in the last 15-20 years, or maybe about 30-40 years. There is so much more computation to chemistry than chemistry itself in the last several years, or maybe even several decades, that some of these theories look very primitive and very naive, but they are not. The fundamental aspects that went into these theories is worth revisiting and worth looking at again and again. So we shall look at the molecular orbital method to start with, and then come back to the VB theory later. Okay. So my lecture today will contain a bit of description of the MO theory, and out of that how the VB approach can be extracted, and a bit of calculations on the wave functions, the psi, and finally as we move further, we calculate energies, the orbital energies or hydrogen molecular energies, and then we shall look at the properties, that is pictorial representations of these systems. Okay. So let us start with the MO approach by first considering the hydrogen molecule as the hydrogen molecule ion H2 plus an electron, assuming that the electron repulsion is minimal. Is not so important as to change our fundamental description of the orbital of the electron being the 1s orbital. The 1s orbital of the hydrogen atom is an eigenfunction for the hydrogen atom electron orbital, the Hamiltonian, electronic Hamiltonian. It is an exact eigenfunction in the absence of any external magnetic fields, and therefore it serves as a starting point for many descriptions. The moment you have two electrons in a system, like for example helium atom or hydrogen molecule where you have also two nuclei, the description of the electronic levels or electronic structure in a molecule as 1s, 2s, 2p, 3s, 3p, etc., that description is an approximate one, is probably good as a zero order approximation, if I may quote perturbation theory as an example. They are not exact eigensolutions. Therefore, as a starting point, if we are using the hydrogen molecular ion 1s orbital, and we assume that there is one more electron associated with this hydrogen molecule ion, so that the hydrogen molecule is visualized, then what you would expect is the wave function for the 1s electron, for the electron in the hydrogen molecule ion, and the wave function for the electron as it approaches the H2 plus to be independent of each other. And if you put the electron 1 coordinate as or a or 1, let me or 1, and the electron 2 coordinate as or 2, what one can expect is, in the same sense as the particle in a 2D box from a particle in a one dimensional box, when the dimension increases or when the number of particles increase and when the particles do not interact, the overall wave function is the product of the wave functions of the non-interacting particle, and the overall energy is the sum of the non-interacting particles. So in that sense, if we have to write SI molecular orbital for hydrogen molecule, we may start with this 1 by root 2 into 1 plus SAB times phi 1 SA for electron 1 or 1, and the same electron 1s A, 1s B, same electron in the 1s B orbital times the wave function for the second electron, in which everything is the same except R1 is R2. So that what you have is 1 by root 2 times 1 plus SAB times phi 1s A R2 plus phi 1s B R2. Okay. So that the overall wave function consists of 4 terms, namely 1 by 2 into 1 plus SAB times, let me write it in a slightly different order, not in the order in which you normally do the multiplication, but let me write it as 1s A R1 phi 1s B R2, one of the terms that come out by multiplying this and this one, and likewise we will do the multiplication of these two, phi 1s A R2 phi 1s B R1, and then we write the remaining terms, namely phi 1s A R1 phi 1s A R2 plus phi 1s B R1 phi 1s B R2. Okay. The reason for organizing it this way should be clear in a few minutes when we discuss valence bond theory, but let us look at these terms individually. So we have a linear combination of the 2 electron wave functions, the basis functions, the 2 electron wave functions such that electron 1 is associated with atom A and electron 2 is associated with atom B, as you have seen in the highlighted portion here. Now let me change the highlight and look at the same term here, highlighted with a different color. You see that it is like electron 2 associated with the 1s atom, 1s orbital of atom A, and electron 1 associated with the 1s orbital of atom B. If you take the square of the coefficients, the linear combination coefficients, they represent the probability that the electrons are such that electron 1 is in the 1s orbital of A, electron 2 is simultaneously in the 1s orbital of B, and vice versa. That is what these individual terms mean, and that is a sort of a localized picture. You are assuming that the electron 1 is not perturbed by the fact that electron 2 is associated with the other atom. What you call as A or B is your label, my label. Atom 1 and 2, electrons are indistinguishable, the nuclei are indistinguishable. Therefore these two the two highlighted orbital contributions have to be exactly the same level of contribution. Now look at the next 2 terms that I have written at the bottom. Okay, let us highlight it with a different color. The square of the coefficient associated with this orbital essentially tells you that electron 1 is in the 1s orbital of atom A, and electron 2 is also in the 1s orbital of atom A. It looks like the hydrogen atom B has lost its electron, and that both the electrons are now associated with the atom A. It is like a H minus H plus, if I may say so. The system is H1 minus, so let me write this, H1 minus and H2 plus. The moment I say this, you will immediately notice that the term I have left out without any description corresponds exactly to the same as the previous one, with the minus and plus getting interchanged, H1 plus and H2 minus. What is important is that all these 4 contributions in terms of probabilities of finding the electrons in the respective orbitals of the respective atoms, if you look at that, because the squares of the coefficients here, what is the square of these coefficients? It is 1 by 4 into 1 plus SAB whole square, that is the same number, you add it 4 times, okay, with the appropriate normalization constant. So you have that all these 4 are equally weighted, that is the possibility that the electrons are equally shared by both these atoms, and the possibility that the electrons are likely to be found in one atom absolutely certainly versus the other, both possibilities are weighted by the same level or to the same degree, and that seems like a little bit far fetched. And therefore, if we argue this on the basis of what we have written down and calculate the energy for the hydrogen molecule, we must expect an energy quite different from what the experimentally obtained minimum, or what is called the exact minimum. So the ionic contributions, as you would call them, this is the ionic contribution, are weighted by the same amount as the covalent contribution, as you see here, covalent, and that is not a very comfortable picture if we were to assume a molecular orbital theory based on 2 non-interacting electrons, and then we take the product of the electrons together and then find out. Now this is coming from one end of the approach. Now valence bond theory, which was proposed by Heitler and London, also starts with the idea that hydrogen A with its electron 1 and hydrogen B with its electron 2, as they approach the distance of what is called the closest approach and the distance of minimum energy, at some point obviously they form a bond, and therefore the energy is the minimum, and the valence bond approach assumes that the wave function for this system should be expressed as the wave function for the 1s electron in atom A, R1, times the wave function for the 1s electron in atom B, or 2, but because the electrons are indistinguishable, the valence bond approach will have to logically correct this by including 1s A or 2 psi 1s B or 1. Which electron is which? When they are close and when the molecule is formed, we cannot distinguish the electron, and therefore these are the 2 contributions, a linear combination that we can think of, and the valence bond theory starts with this as a the what is called the a variationally correct approach. Okay. In principle you can write this as C1 and a C2 if you wish to, but again, as we have in the case of hydrogen molecule ion, there is no reason to suspect C1 and C2 to be different from each other except possibly for a minus sign. Okay. So this is the starting point. So where do we begin? Should we begin at this point, that is the psi VB, or should we study the psi MO? Well, before I give you the answer, in fact we are going to look at the answer, the problem using both the methods. Let me just also point out that the moment you write the psi valence bond like this, the wave function normalization, if you are looking at psi 1 2, okay, VB, this is essentially psi 1 2, VB 1 2. Okay. psi star psi 1 2, since these are all real orbitals and the coefficients we assume are real, we can write psi 1 2 d r1 d r2 integration over both the electron coordinates. The normalization of this wave function leading to 1 must give us this condition, namely let us write this as c squared times psi 1s a r1 plus psi 1s b r2, oh I am sorry, not a plus, psi 1s b r2 plus psi 1s a r2 psi 1s b r1 whole square d r1 d r2 integration of all the three directional coordinates of the electron 1 and the electron 2. That is the total space for both the electrons, and that should be 1, which tells us immediately that we can write this as 4 integrals. So expand this, we will get 4 terms, c squared, the integral psi 1s a r1 squared d r1 times psi 1s b r2 squared d r2, that is the first term, and the other 3 terms are the integral psi 1s a r2 squared, but let me do that with d r2, and psi 1s b r1 squared and integrate that over the d r1. So these are all the integrals of the atomic orbitals normalized, and then you have the term which is what I have done is a square plus b square, this is a square and this is b square, and then we have so if we call this a and b, this is 2ab is what we have. So therefore twice the integral psi 1s a r1 psi 1s b r1 d r1, this is one integral involving the electron coordinates of r1, and the other integral is psi 1s a r2 psi 1s b r2 d r2, okay, and this should be equal to 1. So what should I have? I should have a bigger square bracket here covering this c square, okay. So let us do that, okay, that is what this is, okay. So what we have is the first integral is nothing other than the atomic orbital normalization for electron in atom 1 and electron in atom 2. So that product is 1 times 1, and likewise the second integral we just call r1 and r2 as coordinates. So if it is integrated over the entire coordinate r2, therefore psi 1s a r2 whole square d r2 is the same as psi 1s a r1 square d r1, because all the 3 dimensional space is covered, therefore this is also 1. And this you have recognized immediately as the overlap integral that we talked about in the last 2 lectures. One is a r1, one is b r1, that is electron 1 in one is a and one is b, therefore the 2 orbital overlap integral, and what you see here is s squared, this is an s, this is an s, therefore the normalization constant for this problem is c squared 2 into 1 plus s squared, that should be 1, and therefore c is 1 by square root of 2 into 1 plus s squared. So what we have therefore is the wave function psi vb of 1 2 is 1 by square root of 2 into 1 plus s squared times psi 1s a 1 r1 psi 1s b r2 plus psi 1s a r2 psi 1s b r1. So if you go back and look at the molecular orbital picture that we discussed, you see, if retaining only these two colored terms, the blue and the green and the yellow term, you see that is going to be a small problem with respect to the normalization constant if we keep only these but neglect these. That is exactly what we did here. So if we start with the valence bond orbital, we have this as the overall electron orbital for the 2 electrons. But there is still one more problem. This is not satisfying the antisymmetry principle of the 2 electrons. Now we have 2 electrons, therefore it is important for the wave function to be overall negative if the coordinates of both the wave functions, both the electrons are interchanged. So if I do a permutation of the electrons 1 and 2 on psi Vb 1 2, obviously I violate the Pauli's antisymmetry principle. Therefore this picture is not a complete picture. The 2 electrons, when they are together in an orbital system, you have to worry about the exchange of both the space and the spin coordinates, and we have not included the spin in this part. If we have to include the spin part should be antisymmetric because the space part is symmetric. Remember, if you interchange R1 and R2, if you interchange R1 and R2, you are going to get exactly the same wave function. Therefore the wave function is symmetric. The electron being a fermion, that is not what we want. We wanted the electron wave function to be antisymmetric to the interchange of the 2 electron coordinates. Therefore it is important to have the spin of this psi Vb 1 2 to contain, to be replaced by psi Vb 1 2 times a spin function phi spin 1 2, and because this is symmetric as we have chosen, it is important for us to have this as antisymmetric. Therefore the wave function that we choose must be psi Vb 1 2 multiplied by 1 by square root 2. You remember the antisymmetric spin wave function is alpha 1 beta 2 minus beta 1 alpha 2. Okay. This is a singlet state. Okay. On the other hand, if we take the linear combination of psi Vb, let us call this plus, and if we take the linear combination minus, which we call as psi 1 s A, which we write psi 1 s A or 1, we write this as, we do not need the constants, I know what this constant is, it is easy to verify that it is 1 minus s square into square root 2, you will get the combination psi 1 s A or 1, psi 1 s B or 2 minus psi 1 s A or 2, psi 1 s B or 1. If we do this, the spin part, the psi MO, psi valence bond orbital of 1 2 should now be replaced by psi Vb minus times a symmetric part which is alpha 1 alpha 2 for the 2 spins, or 1 by root 2 alpha 1 beta 2 plus beta 1 alpha 2 or beta 1 beta 2. Any one of the three is as good as the other, because what we have is the spin part is symmetric with respect to the interchange, and in the absence of interactions of the electron spins with each other, or the spin with the electron orbital, or with an external magnetic field, all these three states are degenerate, and therefore you see that this is called the triplet state. The antisymmetric linear combination of the spatial orbitals of the electrons has to be associated with the triplet state of the pair of electrons in their spin quantum numbers. So these are things that one has to keep in mind, but for the calculations that we are going to do in this lecture and the next lecture, we are not going to worry about the spin part of it. Therefore the spin part is not going to change the energy levels by any means, but it has to be kept in mind that it is there, and the two electrons are either paired, as you might normally would like to imagine, in an antisymmetric combination with a spin 0. The spin 0 essentially means spin up and spin down in the same orbital, and now you have the Pauli's principle of all the 4 quantum numbers of the 2 electrons not being the same, because a spin quantum number of one of the electron is a plus a half, the other electron is a minus a half. So the antisymmetry principle is satisfied. Whereas if you have the 2 electrons in the 2 different orbitals, it does not matter whether they are like this or whether they are like this or whether they are like this up and down. Okay, it does not matter up and down or this way, that way. That is what we call as a triplet state, and that is, of course, we will find out that it is a very highly energetic state, and therefore it is not a bonding orbital for our purposes. So the valence bond theory, when we introduce this linear combination, which is a truncated linear combination from this, from the molecular orbital theory, keeping only the covalent contribution in the chemical sense, if we do that and make amendments for the S by writing this as 1 by square root of 2 into 1 plus S square, we have now a wave function, and that is a proposed wave function. We calculate the energy of the system, and that is the valence bond orbital energy. So let us proceed with that calculation in the remaining time. We will come back to molecular orbital theory later. Okay. So what is the Hamiltonian for the hydrogen molecule? Hamiltonian for the hydrogen molecule. Of course, we need this classical picture of having the 2 electrons, not a parallelogram exactly, but it is 2 electrons in 2 arbitrary positions. This is the nucleus A, B, electron 1, electron 2, and if we call this as the coordinates R1 and R2, we have, this is electron A, so we call this RA1, and this is RAB, similar to our previous notation. This is R12, the electron classical charge, point charge, the distances between the 2 point charges, and then we have RA2, electron 2 from the nucleus A, electron 1 from the nucleus B, we will write this as RB1, and the electron 2 from the nucleus B as RB2, and once we have written this, the Hamiltonian is within the Born Oppenheimer approximation of not worrying about the nuclear kinetic energies. So we have minus h bar square by 2 me, we have del electron 1 square, whatever is the coordinate that we need to put in, and electron 2 square for the kinetic energy of the 2 electrons, and the potential energy is now going to be a sum of 4 attraction terms, Coulombic attraction terms, electron 1 with the nucleus A, electron 1 with the nucleus B, electron 2 with the nucleus A, electron 2 with the nucleus B. So you have 4 electron nuclear attraction terms, and then we also have 2 electron and nuclear repulsion terms, electron 1 with electron 2 and nucleus 1 with the nucleus 2. We will include the nuclear repulsion term in our calculation because we want to calculate the hydrogen molecule energy as a function of the internuclear separation between the 2 hydrogen atoms to find out what is the minimum and where is the minimum and what that distance corresponds to, and how does it correlate with the experimentally determined the bond energy and the bond distances. So to include those terms, we have to write minus E square by 4 pi epsilon naught and the Coulombic attraction terms are 1 by r A1, 1 by r A2 plus 1 by r B1 plus 1 by r B2, which are the distances of the electrons 1 and 2 from the nucleus A and B. Okay. And the last term is of course minus E square by 4 pi epsilon naught 1 by R12, the there should be a plus here, the internuclear distance, inter-electron repulsion, electron repulsion, and the nuclear repulsion or EB. Okay. So this is the Hamiltonian. Therefore, the energy that we have to calculate, the average value for this psi VB with the plus combination, neglect the spins, orbitals at the moment. It does not matter, even if you put that in, the spin coordinates are independent of the spatial coordinates. So you will write 1 by square root of 2 alpha 1 beta 2 minus beta 1 alpha 2, the ket times the bra state times the ket state, and that of course is normalized already. Therefore, the antisymmetric state normalized to give you 1, and it disappears from the calculation because the Hamiltonian does not contain any spin orbit interaction. So it is pedantic to include or not to include, but it is important to remember that it is there, otherwise all the calculations are technically wrong because the electron wave function does not satisfy the Pauli principle. So let us write this energy as the integral. Okay, let us have the molecular the normalization constant 1 by 2 into 1 plus s square, that is the psi star psi normalization constant, and then we have the integral psi 1s A or 1, psi 1s B or 2 plus psi 1s A or 2, psi 1s B or 1 times the Hamiltonian, which is minus h bar square by 2 m E del E1 square plus del E2 square minus E square by 4 pi epsilon naught times 1 by r A1 plus 1 by r A2 plus 1 by r B1 plus 1 by r B2. Now, having written this, let me perhaps rewrite this in a slightly different way. Okay. Let's do it somewhat differently. Okay. To get the picture that we will simplify these energies very quickly. So let us write the del E1 square, and let us write the term corresponding to E square by 4 pi epsilon naught or A1 as one set of terms. Then we have minus h bar square by 2 m E del E2 squared minus E square by 4 pi epsilon naught or B2, and then write the remaining terms, namely minus E square by 4 pi epsilon naught 1 by r A2 plus 1 by r B1 minus 1 by r12 minus 1 by r AB. All of this as a Hamiltonian acting on the wave function on the right, which is psi 1s A or 1, psi 1s B or 2 plus psi 1s A or 2, psi 1s B or 1, and integrated over both the electron variables, namely dr1 3 dimensional integral dr2. This is r1 square theta sin theta 1 dr1 d theta 1 d phi 1, and likewise for the r2 square it is r2 square dr2 sin theta 2 d theta 2 d phi 2, except that we have to define the thetas and phis carefully, and therefore the evaluation of some of the integrals in this in the way in which it is written, you would see that it involves 2 electron coordinates centered on 2 nuclei, particularly for the R12 term, the electron repulsion term. So you are going to get more complicated integrals to calculate, but for the hydrogen electron wave function with the 1s orbital function, some of these electrons can be exactly calculated, and I will do that in the assignment later on. But let me stop at this point before expanding this any further, merely because from this point onwards the calculation of the energies, we need to apply the same symmetry and the labeling problems that we had with the hydrogen molecule ion in seeing that certain orbitals are exactly the same as certain other orbitals, certain integrals are exactly the same as certain other integrals, and therefore you have to do a counting carefully, and that we will start afresh in the next lecture. But let me just summarize what I had for today's lecture, that the hydrogen molecule system that we are studying, we are starting with the premises of the valence bond approach, namely that the electrons are localized, which means electron 1 in orbital 1, electron 2 in orbital 2 of the 2 different nuclei, and because the electrons are indistinguishable, an interchange between these 2 coordinates is as much important as considering only one term, and therefore there is a weight of these 2 being put together. We have used a linear combination psi 1s a R1, psi 1s b R2 that you see here in the screen, plus psi 1s a R2, psi 1s b R1 as a starting point. Then we also talked about the spin of the 2 electrons, because the overall wave function of the 2 electron system must be antisymmetric to the interchange of the coordinates of both the electrons or the interchange of both the electrons. And so when the spin and the spatial coordinates are interchanged, it is important to have a symmetric combination of the linear combination to be associated with an antisymmetric combination of the spin wave functions and vice versa. And then we just wrote down the hydrogen molecule energy expression, but we have not calculated. Our starting point for the next lecture would be this integral, namely what you see in the screen. So we will start from here and we will calculate this. Until then, thank you very much.